A warm welcome to everyone to part 3 of the OPC UA Inside Out webinar series. It seems we have traveled quite a bit of journey together since we started this series. From the initial days of the uncertainty around COVID to a settling phase and now slowly inching out into a new normal. Glad to have so many new faces as well today. We have folks from 10 countries the last time I checked in the webinar today. These are primarily OEMs, industrial software companies, and also a few end industries. Again, a special hello to our listeners in North America. Most of you are likely listening to a recorded version of this webinar. My name is Anand Taparia. I take care of marketing here at Utthunga. In our earlier webinars, we have covered the technical and foundational elements of OPC UA, and then graduated to understand the relevance of OPC UA in the embedded and low footprint devices. Today's webinar is titled Edge Gateway. In fact, it was titled Edge Gateway. Allow me to recreate the context just a little bit. Quite a few of you responded to us saying you wanted the broader topics around edge to also be covered and just not the gateway part. That made a lot of sense to us, and accordingly, today our speaker is covering what is edge, why do we need edge at all, and the relevance and benefit of OPC UA in the edge. Just a quick introduction on Utthunga. Next slide, please. Great, thank you. So we are an industrial software and hardware services company, partnering closely with OEMs in the industrial world to build products and solutions from concept all the way through the life cycle of the product. Be it enabling field devices or assets to be smart, or building configuration and calibration software, or highly sophisticated software and hardware systems, we leverage our rich pool of engineers to co-build products and solutions with our customers. We offer services in application development, embedded services, IIoT, and verification and validation. Our services are targeted to OEMs and end industries in process, factory, and power domains. Next slide, please. These are a few standards bodies we closely associate and work with on protocol and connectivity. Protocols form the foundation of how we started as a company, connecting field devices and assets to the hardware and software systems above. Our association with these consortiums, and importantly the OPC Foundation, is rooted in our commitment to build interoperable industrial systems. With that, I would like to introduce our speakers for today. Next slide, please. Thank you. Rushendra Babu, also referred to as Rushi internally. Rushi is our CTO and has close to 2 decades of experience in product engineering, cloud computing, and enterprise applications. At Utthunga, Rushi provides leadership in the area of digital transformation, where he is responsible for defining the strategy, solutions, partnerships, and implementation roadmap. He is very well adept in leveraging both mainstream and emerging technologies, enabling us to provide value-added solutions and services to our customers in the domains I mentioned earlier. Next slide, please. Chatrapathi is the Director of Embedded here at Utthunga, also an active member in the OPC Foundation working group, and has contributed in creating use cases for OPC PubSub on small footprint devices. Chatrapathi has a solid understanding of. He has executed several projects with OPC UA Nano Profile, servers with high performance demands, servers with heterogeneous communication requirements for protocols like HART IP, Ethernet IP, IEC 61850, BACnet, and others. Chatrapathi also has a good knowledge of the NAMO standard and the semantic ID, and has worked with different open source and commercially available OPC UA stacks. Just a few housekeeping points before we get started. The duration of the webinar is 60 minutes. We will save the last 10 minutes for questions from you. Please send in your questions using the Q&A icon on the left side of your screen. The slides of this presentation and a link to the video of this webinar will be shared with everyone post the webinar. Request all of you to click on the full screen icon again on the left hand side of your screen to get a good view of the presentation. Before I hand over to Rushi, our first speaker for today, I just wanted to have a quick poll. It'll appear on your screen shortly. Okay, so if you could please select one of the options that are applicable to you. We'll do this for about 30 seconds and I can close the poll after that. Okay, I'll close at this point. So we have an even mix, so in between people who are self-sufficient and people who are looking for some more expertise. And we also have few who probably do not necessarily have a requirement or an OPC, perhaps from an academic exercise. We really hope this session adds to your existing knowledge and gives you a lot more clarity on edge, why edge, and the relevance of OPC to the edge. With that, I would now like to hand over to Rushi. Over to you, Rushi.
Thanks, Anand. Good afternoon, everyone, and thank you all for being here with us today. The way we will go about this webinar is that I will deal with the context of having OPC on the edge. And then my colleague Chatrapathi will delve into more details on the security and as well as on the use cases. So as we delve into the context of OPC, I would like to take this in three different dimensions. The first one being industrial connectivity. So we will go through some industrial connectivity aspects and see how OPC is relevant there. And then we talk about the data considerations. And then thirdly, we talk about standardization and the emerging trends, that are more oriented, where the OPC is a right, very well placed candidate for us, to get into the next industrial networks and next generation of industrial networks. So to start with, what you see is a typical, plant elements. What you have in any plant, like where the raw material comes in, and then all the raw material gets processed, and then a final outcome is produced all under the same roof. So you have the typical control elements like SCADA, PLC, DCS, VFD, which is what drives the entire lines and segments. And then the data is pulled out, and then you have external systems with respect to the automation side of things. They are external. So where you have ERP, MES, PLM, and AMS. And now what we are seeing today is an addition of IIoT solutions in islands. Even IIoT is becoming islanding. So what we are seeing is sensors as there is a lot of brownfield plants. We are people are retrofitting these elements with sensors and then taking the data parallelly to the IIoT systems, and all this put together is what we are seeing typically in any industrial plant. Now, the other kind of system that we look at is a distributed system. A typical example would be an oil and gas company where the wells are geographically distributed, and the produce of the well is once again has to be taken in pipelines, and they will travel for kilometers before they actually reach their storage area. So still, if you consider the whole thing as a plant, the elements are geographically distributed. And when you look at the previous one, the typical network architecture would be more towards LAN. Whereas in the distributed segment, you will have both the local area network elements. Also, it depends, quite some dependency is there on the WAN network elements. So, and irrespective of the kind of plant that we look at, they generally fall under the ISA 95 hierarchical architecture, where you have sensors and devices, where you have control systems, production management, and you have operations management, and then you have business systems. So they are connected hierarchically, and the data flows in the same manner. But given the nature of business, there is a business landscape is changing, and the landscape is about mass customization, and the velocity of innovation as well as obsolescence has changed, or in fact, it has increased. And everybody is under pressure to respond quickly, and new threats are always emerging. And the productivity has to be optimized, and equally the cost has to be optimized. And on top of all this, the regulatory compliances has to be met. Now, the plant architecture has a very, very big role to play in any company to transform and to actually respond to the new challenges. So in this process, rather than having only a hierarchical model, the new hybrid or flat architectures are emerging. Now, physically they might be flat, but logically, there will still be hierarchies. Control elements, control systems will still control the sensors and devices, but they happen to be all sharing the same data bus. So, which gives us a possibility of, many to many interconnections, and those interconnections gives us the good possibility of flexibility, modularity, but along with that modularity and flexibility, we will also get into the challenges of data management, get into the concept, into the aspects of security management, and so on and so forth. So, as this hierarchical model is being matured, a lot of organizations are working to make sure that we have better hierarchical models, and different organizations are working at different levels. So we'll just quickly go through different reference architectures that are being worked out, and the different versions are coming out on them. So one of the very known architecture is the RAMI architecture, which talks about making factories Industry 4.0, and also it deals with the entire product life cycle. So the other architecture which is relevant in this space is IIRA. So when I say IIRA, it deals about connectivity of elements. Whereas RAMI talks about the production of elements, how you can make the factory smart to produce an element, whereas IIR talks about, how do you make these systems that are manufactured, connectable, and they can talk to each other easily. And the third architecture is the Namur open architecture, where you see that the core process control is untouched, and the proposal is to have flat hierarchies or parallel hierarchies where the data is fetched and then all the analytics are done. And the other one that is emerging is OPAS. It is from the OPAF community. Once again, they talk about service-oriented architecture. Once again, talks about how the modular systems can be built. And then finally, we have module type of packages, which is emerging. And they also talk about modular architectures. What is common across all these architectures is OPC. OPC is considered as a choice for all communication. OPC is considered as the right bet for all interoperability needs. That's how much OPC is relied on all the upcoming standards. So this is one of the reasons why OPC is a very right candidate to invest in for the future investments, as majority of the architectures are falling on OPC for connectivity and to bring interoperability into the plant. So that takes us to the next part: edge, fog, and cloud. So let us understand the edge, fog, and cloud from the point of data. When you look at data, there are certain considerations. What we want is the data to be available all the time. We want the data to be actionable. we want to make sure, or we want to be sure that the integrity of the data right from the source to what we are looking at now is not tampered with, and the confidentiality of the data was maintained all through, and the sovereignty of the data is maintained. Now, we may not talk about sovereignty today, but then availability, actionability, integrity, and confidentiality is something that we will touch base upon. Now, these are the functional requirements of the data, but there are some technical requirements or the technical considerations that we have to look into. Some of the data has very high data rate, and the volume of data that gets generated in a plant, with the kind of vision where everything is going to be having a sensor, is going to be very huge. And then we have to talk about connectivity cost, storage cost, compute cost, and then connection reliability. So once the functional aspects of data is defined, and once the technical challenges, technical and commercial challenges are there, now that is where the decision as to where to compute what comes into picture. And that is where the edge, fog, and cloud comes into picture. See, the edge, fog, and cloud are simply computes. They just compute something, but they are divided into different names based upon the kind of data that they compute and where they compute it. Now, if you look at this particular diagram where you have sensors towards your left, and then they are connected to the edges, and then they are connected to the fog devices, and then finally into the cloud. So if you look at it, edges mostly can be looked at as sections. They will be taking care of the sections and the lines in the plant, where they are very close to the sensor devices, and then they are characterized by very high data rate processing. They keep getting data at a very fast rate, and we keep processing data at a very, very high rate, and especially for signal analysis kind of a thing. And then when it comes to the fog, they will be dealing at the lines and the plant level, okay? And where your model executions can happen, or a plant level situational analysis can happen. And then when it comes to the cloud, that is where you have plant and enterprise, where you might be building models and optimizing models and then feeding back to the fog. And also you might be doing a lot of other intelligent business intelligent processing, or you might be connecting to various other exchanges to get the data, and so on and so forth. But there is always going to be an overlap. They cannot strictly be decided like, the edge, fog, and cloud are concepts. Like, if somebody is going to put a very big processor and say that I'm going to do everything in one compute, it is quite possible. But that is not going to be something that is maintainable. That is the reason where, the computes are segregated, so that tomorrow when you want to really upgrade or change, it is easily maintainable. Now, one of the typical examples I'll give from the data point of view is, let us say you are doing a vibration monitoring for a motor, where our frequency of interest would be up to 5 kilohertz. And if you go by Nyquist theorem, probably 2 to 2.5 times is what we are going to sample the data. And if the data is a float, which is going to be of 4 bytes, we end up with 52 KB of data in 1 second. And then that data will become 4.4 GB of data per day. Now, if this data is not processed very close to where it is getting produced, and if this is fed on the network, it will clog the entire network. So that is where, they get processed at the closest point, which is the edge. And the edge might do a processing. Probably it will do an FFT. And when it does an FFT, the 52 KB of data becomes 400 bytes of data. So which is an order of 100 times lesser. And that data is what fed into the network, where it goes into the fog, and subsequently fog does the processing using this outcome data, and then it can be shared with cloud. So to simply say, these are all computes with the different names, and these names are based on the kind of data and the amount of data and the speed and the data speed, and the processing of the data that they are into. Now, the other important aspect is data vocabulary. Like, if you look at this picture, you have three different, machines, and from two different companies, and each of them are supposed to give, something about execution state, position, and what is the tool number that is being used. And since when there is no standard, everyone can talk about the same thing in a different verbiage. So that is what you are seeing here in the brand X. The execution state is mentioned as EXEC, but the brand Y says that it is execution colon state, position colon ABS. So this also plays a very, very important role. The vocabulary of the data plays a very, very important role in determining how well we are placed for modular structures, and this will become evident in the next section as to how the standardization of data vocabulary, how standardization of certain interfaces makes sense, and how OPC is playing a role in all of that. So when you look at a typical network where the data doesn't have any semantic, that means every manufacturer has their own dictionary, and then they are using a multi-protocol communication. This is how a typical components look like. Your CNC1 is connected on a proprietary interface or Ethernet or serial, and then that particular protocol stack will be there. Once the payload is extracted, then the vocabulary has to be mapped to the final application, and then your application processes the data. And if you are talking about two different lines, this is how the architecture looks like internally. And finally, if these guys are talking to a cloud or any other northbound interface, this is how it looks like. Primarily, at least there are too many interfaces on the southbound side, but on the northbound, to a large extent, they are on Ethernet. But only the standardization is on the Ethernet. But everybody can use their own protocol. There could be messaging, there could be web services, and any other custom protocols. And the vocabularies also can be different. And then this is the complexity that we look at. But the moment we adopt a unified communication, the complexity keeps coming down. So now everybody is on Ethernet. And now you have OPC as a communication. So you don't have to deal with multiple stacks, but you may still have to deal with multiple vocabulary. And then the same thing is applicable on the northbound systems also. Now, if you bring vocabulary also into the picture, like the brand X and brand Y were talking about the same parameters in different names, but let us say we introduce a standard like MP Connect into the system, where it is a standard where it says that all welding robo manufacturers or CNC machine guys will use the same name to refer to the same attribute. Now, once such a data has more semantic now the system becomes much more simpler. Now, where is OPC in this? OPC doesn't ever work alone. Here, it has a lot of companion specifications, and it has an MP Connect companion specification where the entire verbiage is mapped to the OPC namespace. And that's how OPC, on one hand, builds, standardizes on the communication, and it also works with multiple industry bodies on the semantics. And then the whole architecture becomes less complex and easy to manage. Once you have such an architecture, now what do you get? Because of the less number of elements, we get reliability. Because of the unified architecture, you don't have to deal really with the different security elements for different protocols. So the security management becomes easy. And everybody, if not everybody, if majority of the players on the same interface, the interoperability becomes standard. We can have modularity, and most importantly, the single vendor dependency is reduced. So that's how OPC enables, in having a standardized architectures. And the other dimension that we should look on justifying OPC on the edge is the trends that are happening. majority of the communication protocols and majority of the work, there is a lot of work that is going on to bring most of the protocols on Ethernet. And quite an amount of work is going on TSN, so that we get time-bound messaging can be done. And you are talking about a single pair Ethernet, and we are also talking about advanced physical layer. All this is about Ethernet, like either it is a single pair or it is going to be a TSN or anything. They're all going to be working on internet technologies, and OPC is already an internet-based technology. So it is a right choice to get adapted when all these technologies evolve, and right to the sensor level. So once it is connected all the way to the sensor, the next is edge, and then next would be the fog and gateways, and so on and so forth. So given this, we can easily deduce that OPC on edge could be of any configuration. It could be on the client side, it could be on the server side, or it could be on both the client and the server. So to recap, I would say OPC is a very right candidate to be on the edge, as it reduces complexity, and it brings the benefits of vendor neutrality, interoperability, and the devices are discoverable. Reliability and scalability are the fundamentals of OPC, and it has coexistence and complementary. Like I was talking about MT Connect, and of course there are a lot of other companion specifications that neatly get gelled into OPC, and then it is a choice. It is a recommendation choice for multiple emerging architectures, and the ecosystem is always growing. And from this investment point of view, you can be assured that it is a very long-term investment. So apart from all this, other key element that has to be considered for having OPC on the edge is security. So this is where my colleague Chatrapathi will talk further. Chatrapathi?
Thank you, Rishi. Welcome, everyone. So we'll talk about security, and then few use cases, typical use cases of edge, and then what additional benefits you get from using OPC on edge. Next slide, please. So there are specific key requirements to maintain the security, or you can call them as goals as well. So these are pretty standard requirements for any security. So authentication, authorization, integrity of the data, so that no one tampered with the data, confidentiality of the data that is being stored on the device itself or edge gateway itself, and also the confidentiality of the data that is being exchanged in and out of the edge as well, and availability of the service and availability of the data, as well as reliability of the connection and of the connection availability and the device availability, and then auditability in terms of different events and different alarms that are being occurring in the system, and then the boot up security, and also to safeguard your device from being upgraded, a firmware upgrade from any unauthorized users. So now we'll look into how some of these key requirements are handled by OPC UA. Next slide, please. So in this slide, these are the key requirements that are key security goals that are chosen by the OPC Foundation, and for each of these goals, what are the different types of threats that are available. So these requirements and goals has become the requirements for creating the security specification for OPC UA, and so by design, the OPC UA specification includes solutions for achieving all these security goals. Next slide, please. So here we have explanation about different security requirements and how OPC UA achieves it. So for authentication, username, password, and then X509 certificate or JWT, like this, different tokens are there, which can be used for authentication. So for authorization, OPC UA provides mechanism to exchange the credentials, but based on the credentials, what does the system allows for that specific user? It is again implementation dependent, and you have freedom to implement that role-based access as per your requirements. Integrity of the data is provided by the secure channel, and symmetric and asymmetric signatures are used to provide the integrity. Confidentiality, the data that is supposed to be stored, like some configuration data or any local storage on the edge, that is not in the specific scope of OPC. If you are storing it separately, you have to have your own encryption mechanism to handle that. That is not fully covered by OPC. However, the data that is being exchanged through OPC UA communications is protected because of the asymmetric and symmetric encryption that is being used for the data exchange. And availability, while designing the OPC UA message exchanges, how the request and response mechanism should work, it has been thought through so that there will not be any unnecessary processing done by the OPC UA applications, so that the system is available in majority of the time. And there are different types of audit log services that are defined in the OPC specification to log different events with respect to anybody trying to enter, trying to connect with the wrong password or even with the expired certificate and so on. Next slide, please. If you are little familiar with the OPC UA specification and OPC UA terminology, this slide again explains the same aspects on how OPC UA specification addresses the security aspects. So with each of the security goals. So for example, the security mode equal to sign, that is something you would know or you would recognize if you are little bit familiar with the OPC UA specification. Sign and encrypt is a security mode where the data gets signed and also it gets encrypted. So similarly, each of the security requirements and security goals of the goals chosen by the OPC UA security specification and how each one of those are handled. So terminology wise, this slide is more close to the standard OPC terms, if you are familiar with it. Next slide, please. So now we'll look at some use cases of using OPC UA on edge. So here on the left side, we have a list of functionalities that are supposed to be handled by the edge. And then right side, you have some common use cases, what you are supposed to get out of it when these functionalities are implemented on the edge. So connectivity to data sources. So this is important because the edge deals with different heterogeneous communications. So for example, in a plant, you may have different devices and different So some devices you may be directly connecting to monitor some data. In some cases, it may be getting through some communication adapters or even through different PLCs, different makes. And so in some cases where you are looking for cross-functional integration, so the protocols are also completely different. So to have connectivity to different heterogeneous communication protocols, that is the one of the functionality supposed to be there in the edge gateway. And it should be, the data must be easily configurable, and the data must be easily integrated into either pushing into a local database or on-premise database server or a cloud application or a cloud-based database or some analytical engine which is running on the cloud. So in both ways, it should be easily integratable. And and fetching the data, it can happen from in two different ways. One is the cloud itself can originate the request and get the data from the device. When the cloud application knows specifically exactly when some event happens, or when based on a specific timing when it needs to get the data. Or in some cases, the edge can continuously send a stream of data. So for both, OPC is suitable. So the client server architecture works in the request response mode, and the pub sub specification, which uses JSON encoding and AMQP or MQTT messaging for publishing the data in pub sub specification. So in both modes it works. And then protocol translation, this is on the northbound, it can connect to any different protocols, and that can include other OPC servers or older OPC DA classic servers as well. So it can connect to different devices with the protocols and aggregate the data and expose the data as OPC UA data. And configuration and manage with respect to this, there can be different configuration methods that you can have on your edge OPC UA server as a method calls of the server. And these methods can be used to configure the edge as well as the underlying devices, and also for management of these devices. We already talked about the security aspects of OPC UA, and this is storage and forward in a typical IoT sense. It is not a store and forward, but however, the OPC has inbuilt historical data access specification. So as per that, the data can be historized, and whenever the client application or the cloud application recognizes that there is a disruption in the connection, so for that specific duration, once it comes back, it can request the missing data, and the OPC server can provide that missing data by responding to the historical data access requests. And based on the data that is being fetched by the edge from the underlying devices, few rules to set a simple threshold based notification systems and threshold based algorithms can be created easily with OPC. And monitoring and diagnostics and health states of the devices can also be created with the notifications for them when they reach a certain threshold, or when the value matches a certain value based on that. And different analytics can be executed on the edge based on the processing power, the amount of data that is being collected. And So the analytics help in filtering the data which goes out. So without any context, simply pushing thousands and thousands of tag values at microsecond speeds and millisecond speeds into the cloud doesn't make any sense. So that's where some basic analytics come into picture, where you convert this huge amount of data into information. So by adding some context and by adding by filtering out or by reducing by deriving some values based on the raw data. And then the portability. So OPC runs on any hardware and software platforms. I have seen implementations from different FreeRTOS and Linux as well as Windows, and different languages has been used to develop OPC. Java, ANSI, C++, .NET, and so on. So, and then we look at the common use cases that can be achieved with the help of these functionalities. So predictive and prescriptive maintenance, where you can predict if a specific device needs a servicing at a specific point of time or not. And then prescriptive is where you can reduce some specific instructions for the service to happen based on different types of learning algorithms based on the data that has been collected over a period of time. Asset tracking and different types of monitoring, like conditional monitoring or health of a specific device or an entire process flow, or you're only interested in monitoring vibration of a specific motor or a specific spindle in a CNC machine, or quality monitoring of the produced products or material. So different things can be monitored. And so digital twin. So digital twin means basically the digital representation of a physical asset, and it can be a very small sensor or a little complex flow measurement device, or it can be a robot, or it can be a CNC machine, or it can be an entire plant itself. So anything can be called as a digital twin. Now OPC UA works with several different organizations to create information models to represent from a very small device. So for example, process automation device information model, which is known as PIDM. So that represents different devices that are popularly used in process automation industry. And then that information model represents such devices in a manner where it addresses many of these use cases, where you can get the data to achieve these use cases. Similarly, there is a CNC machine related information model, and there is a information model between by the working group between CC Link Foundation and then OPC Foundation, to which works for CC Link based controllers to an entire process platform. So creating a digital twin with all these different information models that are available, from a small weighing scale to a huge CNC machine, or even a process or a plant level, it becomes easy with the OPC UA. And with once you have a digital twin, there are different use cases that are possible. So first thing is quality management, and then based on the different inputs and based on the different deductions that are being done based on the data that is collected by this digital twin, you can get ideas for a new product development, or fixing or enhancing the existing product itself with new variants. And you can run different types of simulations on this digital twin, which will be useful for your training of the plant staff, or planning, or when you are designing the process itself. You can use the data which is being captured by a similar digital twin process, uh, or even for an integration of a new machine, uh, or even a replication of some kind of existing process in a different location. So for all these purposes, this helps. And once you have this digital twin, the natural progression is towards autonomy. So once these small devices also started making little adjustments, started making small decisions based on the available data and based on what they have learned so far, that becomes that much easy to uh, go towards autonomy. And replacing any device or any machine, or replicating the same setup somewhere else, it becomes easy with digital twins. And using VR remotely, the any servicing and any repairing can be done. And on live, what is the current state of the machine, what are the values at each point, whether a particular valve is opened in 30% or 40%, everything can be viewed live with the VR technology. Next slide, please. So this is to get an understanding of the cooperation between all the different organizations and between OPC UA. So as you can see, some field level protocols are there, and some engineering related standards are being interoperable with OPC UA by creating information models, and some factory automation standards are being created for interoperable information models and so on. Next slide, please. So here we have three use cases where some of the functionalities that are described in the first slide of the use cases are being handled by these examples. So this is a smart factory example. Next slide, please. This is a cargo fleet example where each cargo ship is fitted with different heterogeneous communications, where from fuel pump, fuel monitoring, fuel consumption monitoring, and the current location of the ship, at what speed it is going. So all these different parameters are being collected and pushed into the cloud. And whenever there is a disruption in the network connection, the data gets stored, and once the connection re-established, the collected data gets pushed. Next slide, please. This is related to water management, where based on the end user consumption patterns, the water flow and the storage tank levels are maintained from the reservoir. Next slide, please. So this is a solar power plant where different solar panels are connected with OPC. So the Modbus data is fed into these OPC gateways, where the gateway runs analytics based on the entire plant efficiency, and compare it against each panel's efficiency, and detects and identifies that specific panels needs servicing, or specific panels cells are damaged to get they're not performing optimally, and so on. Next slide, please. So that is the end of our presentation. We'll go through the different question and answers that are been coming in, and we'll try to answer those. If any unanswered questions remain based on the time constraint, we will answer those via email. Anand.
Okay, so the first I'm seeing here is MQTT versus OPC UA. What are the advantages and disadvantages? Both may have other pros and cons. So what are the use case scenarios from one of them is more, that is in what kind of scenario? So I think, seeking a comparison, pro con between MQTT and OPC UA.
So I'll take this one. So MQTT versus OPC UA. So that doesn't sound right. The reason being, OPC UA PubSub standard itself explains how to use MQTT messaging by creating a JSON formatted message in a standard way. So what you are really asking is, you use MQTT based on your own formatting, your own message encoding format, against using OPC UA's prescribed JSON format, but again with MQTT itself. So MQTT is common in both OPC UA and in MQTT. The difference is the encoding which you will be using. So when you use OPC UA PubSub specification, your message MQTT messages are standardized as per the OPC UA PubSub specification JSON encoding. But when you use a plain MQTT, you are having your own custom JSON formatting, which no one else would understand other than your own devices on the other side.
Okay, I'll speak out the next question. It's from Raj. It says OPC UA also contains the historic DA, data access. How this is defined and accessed via Edge?
And how to read a PK value of trend data. Okay. So as long as when your Edge is running an OPC UA server, the OPC UA client, if it is running on the cloud, it can always request for the HDA data by specifying exact from date and time and to date and time, and the server can respond.
Does OPC UA support all types of PLCs or CNCs, that is makers like Fanuc, Siemens, etc.? Any major limitations?
So different PLCs, there are different PLCs available in the market with OPC already running on them. So using any OPC UA client, you can connect to such PLCs or CNC machines very easily. But if they are running or supporting any different protocols than the OPC UA, then you can still collect the data using that particular protocol specific client application, get the data and expose via your aggregated OPC UA server.
Okay. One other question is around security. Can you tell a little more about security? I think you could perhaps cover it in this.
Hello, Anand.
Yes, Roshi.
So there is one question about fog data rate from one Mr. Kunal.
Yeah.
Okay. So Mr. Kunal is asking, fog data rate is 400 bytes per second. I think it has to be Mbps.
Okay. To answer that question, Kunal, so what I have spoken about is the amount of data that get transferred between edge and the fog. It is not referring to the capability of the data that the fog can handle, but in that particular use case, instead of sending the whole set of data that the edge receives, it can process the whole data, which could be in terms of 52 KB or per second, and then it can transfer only a portion of the data to the fog. That is how it makes sense to segregate elements across the network.
Okay. One other question is, I am planning to build a OPC UA. I'm planning to implement OPC UA into my edge device. What is the starting point? So if somebody wants to start, they've understood quite a bit today, but where do they start?
Anand, to some extent, we have covered some aspects of how you build OPC UA into an embedded device in our previous webinar. And in that, the approach what I have taken is, if you want to build OPC UA into your device, what are the steps that you need to follow? So maybe that webinar will help him.
Sure.
And after going through that, if he have any further questions, he can definitely contact us.
Sure. We have perhaps time for one more question. This is from Namdev. He says, can you please brief on digital twin? I'm still not clear with it.
Okay, so maybe I'll send some reading material to him, to Namdev, with a little more explanation written in an email too.
Okay, one final question, and before it's just about time. How much old historical data can be accessed using OPC UA? This is from Samir Sani.
So there is no actual theoretical limitation. It depends on what is your database size and how far back you have stored your history into your HDA. So once you raise the request, even if the response size is huge, OPC UA can still chunks it out into smaller records, and it will keep sending it.
Okay.
So, yeah.
Great. So with that, we'll end the Q&A round. Thank you everyone for all your questions and participation. There are a few questions that are unanswered, so because of the time constraint, and I'll get back to you via email. It seems we are actually building quite a healthy set of activities. So to wrap up, I just wanted to quickly have one final poll question. If you could please answer this one. It's appearing on your screen right now. So we'll wait for 30 seconds before we close. Okay, I shall close the poll now. So there are just very minimum people with immediate requirement, but quite with a roadmap, interest in OPC UA. I urge you to reach out to us, and we'll also talk to you. And if there's any way we can support you in your journey to build OPC UA into your edge, your application, we will be very happy to. Just before we wrap up, I just wanted to quickly talk about the webinars that are coming up in the remaining part of the OPC UA Inside Out webinar series. The next one on June 11th is on tunneler. This one in some way is a slight deviation if you are following the classic ISA 95 hierarchy. This webinar will cover the integration of OPC DA, the classic OPC, and OPC UA products. Given that the classic products are here to stay for quite a few years, tunnelers will play a crucial role for both flavors of OPC to coexist, and also to ensure a proper transition to and adoption of OPC UA. The next one after that, on June 25th, is on the role of OPC UA in IIoT. With near infinite, in quotes, compute power and storage available in the cloud, the ton of data that is being generated in a typical plant floor can be run through advanced visualization and analytic engines in the cloud. In the last webinar of this series, we covered the connectivity challenges in brownfield projects and the importance of implementing OPC UA ground up in greenfield projects. Please block your calendars. We will be sharing the registration links end of next week. If you want us to cover a specific topic or topics, please email us at marketing@utthunga.com. It's marketing@utthunga.com. Hope this webinar was worth your time and you're walking out with additional knowledge. It has been a privilege for us to host you. Hope to see you all on June 11th. Stay safe. Thank you very much.